engineering students. For our second video this week, I'm going to start with a little bit of outdoor activity. The whole reading this week is going to focus on how things are attached together. There's a lot of different words and phrases. A lot of them are synonyms, a lot of them I might use a little differently, but we're talking about the way that different entities are attached together. So we're talking about support types. This is related to the ground reaction forces and moments and things like that. But because there's all different ways this can happen, this is why we're going to spend this whole video talking about it. And then we'll switch after this live video. We'll go to looking at it on the digital whiteboard in 2 dimensions. And then I'm going to show you how it works in Onshape as well, which is more practice for those of you who are trying to build your Onshape skills. So there's a lot of ways that different objects can connect and relate to each other. If we're talking in 3 dimensions, which is the world that we live in, with crows flying overhead and children screaming all around us, then it's actually quite complicated. But we are going to start there. So first of all, I want you to know that there are 6 degrees of freedom. How many? 6. Okay, 6 degrees of freedom, and that is 3 translational and 3 rotational. Okay, we live in a 3D world. So when we say 3D, 3 dimensions, we are talking about an X, Y, and a Z. And so first of all, any attachment, any connection, and I'll show you what I mean in a second, can slide or translate in those 3 sliding directions. Okay, so we can slide left and right, we can slide forward and backwards, and we can slide up and down. Okay, that's our 3 translational degrees of freedom. Please write that in your notes, degrees of freedom. The other 3, to make up the full 6, that's 3 degrees of rotational freedom. Okay, this is a little tricky, but here we go. We have rotation in one direction. Let's see, we have rotation in the other direction, and then we have rotation in the 3rd direction. Okay, and each of those 3 rotations, they have the axis of rotation, which is that XYZ axis. Okay, so all this should feel kind of familiar with everything that we have talked about, but as I say, I'm going to show you some examples of how things work using that language, that degree of freedom language. 3 sliding, and then 3 rotating. Okay, I've lost track, but 3 sliding, 3 rotating. So let's start with a really simple attachment style. So here we have our tent, and this tent is on the ground, and you can see that the way that it's on the ground is not attached, it's just kind of resting gently, and we call this simply supported. Okay, I don't know if the book uses that phrase, but I'm going to keep calling this simply supported. It's literally just resting there. Okay, it's not bolted, hinged, pinned, sliding, anything like that. It is simply supported. And this simply supported joint has actually has 6 degrees of freedom, like everything, but only one of those degrees of freedom experiences constraint. Okay, and in this case, the only thing that it can't do, the only constraint it has, is the vertical. This thing cannot press through the ground, even if I pull down on it. Now, it can slide left and right. It can slide forwards and backwards. It's happening. It can twist. It can actually, if I push hard enough, it can rotate freely that way, and it can rotate freely this way. Okay? So it's free to rotate in all 3. It's free to slide in 2 directions, but it cannot move vertically. That's the one way in which it is constrained. Okay, this is called simply supported. Let's go on to another kind. Here's a chair. Let's use this right here. On our little magical folding chair, this is Miss Isaac's. Thank you, Miss Isaac. We have a connection between these 2 members. Now this is a hinged or a pinned connection. Okay, hinge, pin, there's probably other ways to refer to that. But you can see we have like a pin. In this case, it is actually a rivet. A rivet is a permanent connection that can't be unscrewed or anything like that. And this one keeps actually everything from happening except one. Okay, where the simply supported one let anything happen except one. This actually is the opposite. This keeps everything from happening except one. You cannot translate, like slide these things apart. Up, down, left, right, this way. Okay, picture the X, Y, Z. This cannot slide in any direction. It also cannot rotate in most directions except this. Okay? It can rotate that way, and that's it. One rotational degree of freedom, and then all the other 5 are constrained. Let me show you one more. Okay, this right here, this is called a collar. Now, a collar connection, this one actually is free. If let's say we like chopped off all the other bits and pieces. This maybe isn't a great example, but if we kind of chopped it all off and set it loose, we could actually swing that around. Okay, it would have a rotational degree of freedom. Can you imagine that? It also clearly has one translational degree of freedom. It slides up and down the shaft, but it cannot slide out in the X, out in the Y. It can only move up and down in the Z, okay? And it can rotate in one direction if we were to cut it loose, but it can't rotate the other 2 directions. So this one has 2 degrees of freedom. 1 translational, 1 rotational, and the other 4 are constrained. Now, when we draw our diagrams, we're going to show those constrained dimensions as being reaction forces. Okay, that's where we're going to have a little force or a little moment showing which is resisting what's happening. For our tent leg, if I draw a picture of this, I'm going to draw one force coming up under that from the ground reaction force, perpendicular, all that good stuff, but I wouldn't show any other resisting of any kind. But let me show you one more to kind of contrast with this. Let's go right here, perhaps. No, all the way over here. All the way over here. Okay, here's another way that we can attach a pole to a ground, but this is very different. This one doesn't want to rotate that way. It doesn't want to rotate that way. If I twist, it really doesn't want to rotate that way. It also doesn't want to slide that way. It doesn't want to slide that way. Do I need to prove this all to you? Is this just not obvious? And it also won't pull up and down out of the ground. This one is the most constrained. This one is all 6 degrees of freedom, locked down, eliminated. So if I were to draw a diagram of that, I would have to show forces in all directions resisting it when some Yahoo is pushing on it and pulling on it like I am right now. Okay, so that is a fully fixed situation between the pole and the ground. And as I say, this is all a little bit complicated. If you keep your eyes on the fact that there are 3 rotational and 3 translational degrees of freedom, there are 6. You can keep track of them every time. We're also going to switch to the whiteboard now, and we're going to keep it in 2 dimensions. Okay, we do not need to do 3D analyses at this level. We're going to do 2D. In the 2D world, we actually only have 3 degrees of freedom total. We have translational left, right, translational up and down, and then we have rotational in that same plane. Okay, and then at the end, as I said, I'll show you the on-shape equivalent of all of this, and that will be kind of cool, and that will be back in full 3D again. Okay, I think we're good. I'll see you on the whiteboard.
Okay, so now that we're able to draw some things, let me quickly show you what things look like in 3D, but then we'll just really focus on the 2D for this whiteboard thing. So let's say that we have some kind of object, just some random object that looks like kind of a asteroid floating through space. What I was saying is that if you have your let's see, if you have your like X, Y, and Z axes. I don't think those colors match to Onshape or SketchUp, by the way. You can have 6 degrees. I want to make sure you see this because I only just said it out loud. 6 degrees of freedom, or DOF, in total. Okay, so we just said that there are 3 translational, which means sliding. That's geometry, language for sliding, and 3 rotational. Okay, so we said that you've got, you can slide that away back and forth. You can slide that away back and forth. You can slide up and down back and forth. Those are our 3 translational. And then we also have the ability to rotate around the x-axis, to rotate around the y-axis, and then rotate around the z-axis. And that just summarizes like everything that can possibly happen to any physical object in the 3D world. Now, I said that we're really just going to focus on, that's 3D, we're really going to focus on 2D only, because most situations can actually be kind of summarized into 2 dimensions and still be very, very useful. So for this one, I think I'll draw like that leg of the tent pole that we were just looking at. Okay, there it is with its little stopper. It's got a little bolt down there, some random holes and things. It obviously continues up. So this object in a 2D world, we really only now have X and Y. Okay, Z is out of the page, but we just don't think about it. We're doing 2D now. So now we should say that we have this back and forth motion, left and right. We have this up and down motion along the y-axis, and then we only have one rotational possibility. Okay, we don't consider the swinging around the y or the x. We only consider like rocking left and right, which is actually around the z-axis out of the page. So technically, once you introduce moments, you are always talking in 3 dimensions, but you can kind of see what I mean. It's happening in this flat plane of the page that we're working on. So what we're saying with the tent pole is that there is no constraint left and right. Like there's no reason why it can't slide left or right. Let's pretend friction doesn't exist, just to begin with. Because we're saying there's no real friction to consider, because this thing can slide left and right, we don't draw any kind of resistance that is horizontal. Okay, no horizontal reaction. Now, if you started taking into account friction, you might do that, but just forget that for a second. That tent pole can also rock left and right. It's not likely to do so very much because it's all, there's the whole superstructure, but if you forgot all the superstructure and the canopy and everything and you kind of disconnected that, there'd be nothing stopping this tent pole from just, rocking left or right in the wind and falling over. So there's actually no moment reaction either. There's no resistance to any moments that might happen. Like if the wind blows, creates a force, there's a distance, that is a moment. That's what makes it rotate and fall over, and this wouldn't stop that. And then we were saying the one thing that does happen that is very important, and maybe I'll label it with like RY. Okay, that's R for reaction, and then subscript Y is for the vertical direction. Other terminologies could be RV for vertical, Probably RY is a little more helpful because then if you do switch to 3 directions, you've got XYZ. But we do have a vertical reaction regardless. Now, because this thing is just simply resting, oh, sorry, I should have said this at the start. This is what we called in our first part of the video, we called this simply supported, it is just simply resting. Now, if you look at your textbook, and I'm opening mine up right now, you can probably hear that, he does actually refer to something that is slightly different. Similar enough to kind of be interchangeable, but not exactly the same thing. So this is pretty close to what he's referring to as a roller support on page 178. A roller support, and that's how he guarantees that there is no friction side to side. If you imagine this thing was resting on like a marble or a set of roller skates or something like that, and it could freely roll left and right, that's why he calls it a roller support. And those do actually happen. If you go and climb under a bridge, like just a regular old bridge, what you'll actually see, oh boy, that was weird. What you'll actually see is they put a little support under one end, and then on the other end, they often actually put a literal physical rolling circle of some sort. Sorry, I should be more obvious here. That this side might be an actual pin or a hinge, but on the other side, they don't pin it or hinge it or bolt it or anything like that. You might expect that they would bolt a bridge at both ends. They actually don't. They only pin it or hinge it at one end, then they let it freely roll back and forth on the other end, and that allows for expansion and contraction. For when the bridge gets hot or cold, it actually does change its length. It gets longer and shorter, and that lets it change around freely. So that is one of these cool little roller supports. They do happen, but simply supported is really the same idea. Something that is simply just resting right there. Close enough that we'll just use them interchangeably. Only difference is horizontal friction. Now, this one is also really important to understand because it does happen so commonly. All these things we've been doing, like a table resting on the floor, a crate resting on the floor. A lot of the free body diagrams and examples we've been doing all semester long are just like this. They're not bolted, fixed, anything complicated, not pinned or hinged. They're just sitting there. For furniture, it's especially applicable. So yeah, use it all the time. I'll be showing you how to use this more next week, by the way, how to set up your equations and diagrams more carefully. But for now, we just want to go through these different types. The next one is the pinned or hinged kind of one, and in the first part of the video we pointed to the little cross members on Miss Isaac's chair, and we said these two things have a little rivet that connects them, and so they can rotate freely. Let's get a little more into that now. Now, this is also mentioned on page 178 and 179, and he does call it a pinned support. So the pinned support, when like something is stuck to the ground, I guess I just kind of mentioned it right there, and this is just like the diagram in the book. It's when you've got an object that really is truly literally hinged, pinned, just like that. It might be the middle of a seesaw, it might be the end of a bridge, like I just said. It could be a link in a machine. It could be like a like a steering link in my kids' little go-kart that they love to push around. Really, it's very, very common. Things that can rotate, but that's all they can do. And so what we said here, out of our 3, remember we have 3 to consider, x, y, and then the red moment there. We do get a vertical reaction force. Okay, if you grab this link and you try to like slide it up into the air, okay, and contrast this with that tent pole. If I could pick up that tent pole and lift it up into the air and nothing stops me. But if I try to pick up the link, not talking about rotating it, but trying to like slide it up into the air, it is going to fight me. And so what I do is I do have to draw again that reaction force. And this is the force that can potentially fight me if I try to do something. We also have a horizontal reaction force that will react against horizontal motion. If I try to pull this thing left and right, it just won't do it. Okay, we pointed that out again with the chair, that we really can't do anything at all with that particular connection except rotate it. Notice with both these reaction forces, I don't know what they're going to be yet, because they only like emerge in response to applied forces that would happen to the object. Okay, if I push down on this mechanical link here, or if I pull up, or I pull side, or I pull at an angle, if I start twisting it, all those different actions are going to produce slightly different reaction results as they try to fight what I'm doing. If I push harder, they're going to push back harder. Okay, if I push the opposite direction, they will switch and do the opposite direction. So these are Rx and Ry. They're kind of just placeholders right now. And I also made them positive placeholders, like in the positive XY direction. Just try to keep positive numbers in all likelihood coming up later. But they're just staying there ready for if I need them. Sometimes you don't need them. If I don't pull sideways on this link, the horizontal reaction force won't light up. It won't appear because it's not needed. But it's there as needed, so I do need to consider it. But what's really important about the hinge one is that there is no moment reaction. There's no moment resistance. If I take this link and I start to swing it up like a seesaw, it's not going to stop me. It's not going to stop me like it stops me from sliding. Excuse me, grabbing a bit of coffee. Okay, I think that's pretty straightforward. Let's go on to the next very, very common one. And this is what we call fixed. And that is the language in the textbook. Other terms that I have seen for this include things like welded, attached, I don't know, bolted, referring to like the actual physical means of doing that. When you weld 2 pieces together, this is what you get. When you bolt 2 pieces together, this is what you get. Fixed. This is like the pole fixed in the ground. In fact, let me draw that pole. And the way that we show this is we actually draw like a little bit of ground, and then we do these little shading, hatching marks. And every engineer does this in every country that I've seen. That's how you show something fixed. That symbol even appears in Onshape. When you fix something in an assembly, you get that little like ground representation with little shaded lines under it. Universal language. And so what this does, this says that if you try to pull up or push down in this thing, it's going to stop you. There is a vertical reaction force. If you try to push sideways, like slide, it's going to stop you. There absolutely will be that right there. And if you try to twist this thing in the ground left and right, you will get resistance. Okay. Now, what I'm going to do, I'm going to go with standard sign convention. Those are all the standard positive directions. So I'm just going to draw this. I don't know what I'll call it. I'm just going to call it M for moment. you could call it R subscript M. You could even call it M subscript Z to show that it's the axis of rotation is coming out of the page right at you. But point is that you label it with an unknown amount. So this all says that if I start applying loads, if I start shaking on this thing, pulling on it, those are the three that can develop in our two-dimensional analysis to stop me. And this, by the way, is very, very similar to the diagram on page 179. Only difference for his diagram, he did his horizontally, I did mine vertically. He decided to do MH. I think that's bad nomenclature, actually, the H. And he did it in the opposite direction than I did. But the point is that it's there, and it really doesn't matter which direction, which sense you do it, because the sums will all work themselves out as long as you are consistent. Okay, he goes through in the textbook a bunch of other types of support conditions. He talks about inclined supports on rollers, which I think is kind of specific, but he includes those. That does happen. Then he goes into three-dimensional stuff on page 181. He talks about a ball and socket. He talks about a collar assembly. The collar on page 182. That's the exact same thing that was on Miss Isaac's chair that I pointed out. It can slide up and down. It could rotate, but it can't translate in two of the directions. And it can't rotate in two of the directions. Now all of this, the fixed, the pinned or hinged, and the simply supported or roller support, these are so critical because we want to draw free body diagrams of the things that we build, whether it be the whole thing or we focus on just like one part of it at a time. You still always end up drawing these free body diagrams with these reaction forces, and the reactions that you draw in will actually affect the outcome. They will actually define when and how an object is going to break, for example. Like, believe it or not, this might sound funny, but let me show you something. Let's say that you were building a machine. Let's say that it's like some sort of machine or something, and you, I don't know, or maybe it's like a metal bike frame, like a bike rack that's built into the ground, concrete into the ground, and it's like all welded. Let's say it's like one continuous piece, and then you have three parts, and you cut three pieces of steel, but then you weld them back together, and then you cement it in the ground. Everything here is all fixed supports, and even the individual, the cross beam compared to the vertical parts, they're all fixed compared to each other. They're all welded together. If you pull down on this with a particular force, hold that in your mind for a second. Let's say it's like, I don't know, let's say 1,000 newtons you pull down. And then your friend, assuming you have friends, builds a slightly different bike rack. This one, I hope you can tell what I'm doing. Wow, my pen is going a little bit nuts here. This one actually has hinges. Okay, instead of welding at those transitions from vertical to horizontal, let's say that it was hinged, and then we pull down with the exact same force. The funny thing is that while the upper one is going to stay more rigid, and you won't get as much like slight changes in deformation in the shape of the body when you pull down, the lower one will actually experience less internal force along that top beam, because because we used hinges and not fixed, it actually changes the outcome of the analysis. So my only point here in this little mini illustration is that it really matters that you choose your supports and your connection styles. In any analysis, you've got to make them as close as possible to what is actually happening, because it completely affects the outcome. If you choose the wrong supports, like let's say someone, you're a junior engineer working in a company, and someone has this product and they ask you to analyze, what is happening in this top beam, and you modeled that as being fixed instead of hinged when it was actually hinged, your results would just be completely wrong. You get a whole different stress profile along the length of that beam, different like max stresses. Everything you do would be a complete waste of time. So you've got to understand supports, understand these support constraints, and how and when to use them. And it's not tricky, you just got to match it to the actual physical reality as much as you can. Here's another little mini example as to how this is going to come up for us. Let's say you're building Mrs. Jones' standing desk. Here it is in all of its glory. It's got a little cutout shelf. Maybe it's got a little open shelf here, just making this up. There's a nice little wooden surface for a computer. And then let's say that you did a design that had, I don't know, this is kind of a dumb idea, I guess, but maybe it's not. Maybe you'll use this. Let's say you created a hinge, and you had like a little, maybe this is a good idea. We might be onto something. I'm trying to get rid of that under. Ah, boy. Okay, so you have like this hinge thing, and here's your wooden surface, but then let's say that it can like flip over. So in its alternate configuration, it actually like sticks out over the edge to create like a quick little platform for the iPad. Yeah, it's not a stupid idea, I guess. Kind of like instantly doubles your workspace. I actually kind of like that. And the reason why this thing wouldn't flap and fall all the way down is because you see how the hinge, it has a little bit of an offset distance right there. So the support would actually be resting right here on the edge of that desk, while also being hinged right here. So you would actually draw a two-dimensional analysis of this, something like this. You might say, okay, we have like this is the main support. This is your hinge. It says hinge, not binge. All right, that's your hinge, and then right here, you would just have a simply supported, or if you want to call it the roller support, that's fine. I know there's no roller there. The point is that it's just like resting on the thing, and there's no horizontal friction left or right. And then you might show like, here is the weight of a laptop on this at a particular distance out, and then you'd have to work out your reaction forces. Let me do it in blue, just because there's a lot of black happening here. Okay, so I might say, here is this reaction force number 1, Rx1, and because this is a hinge, this also has a reaction force and also a horizontal. Oops, that should be Y. Oh my goodness, I completely messed that up. Sorry. Getting my X's and my Y's completely wrong. Sorry about that. Okay, so this would be the free body diagram you would draw of that particular part of the piece of furniture. Okay, and you see that I used two of those three things that we've been talking about. I used a hinge support constraint where there is a hinge, and I did a little simply supported one with just the vertical support reaction force where it was like just resting on the edge of the desk. And so next week I'll show you how you actually set up all those equations, do this more carefully, and end up by finding out what are all these mysterious forces. Okay, because what they end up being really affects like the knowledge of, is this thing going to break? What are the internal stresses? How thick do we need to model this this piece of wood as, so that it won't break if someone leans on it? Okay, it all comes down to those reaction forces. All right, we're going to leave it there. For the whiteboard, I'm going to switch over, and hopefully this segment won't be more than about 10 more minutes. I'm just going to show you in Onshape how these same ideas in 3 dimensions work. And part of my plan here is just to give you more experience with Onshape, kind of look over my shoulder as I show you different things. This will be all working in the assembly area and showing how to connect things together with different types of connections that still use those, as we said, the, where are we? 6 degrees of freedom in total, 3 translational, 3 rotational, and how each different type of constraint allows some of those 6 and disallows others of the 6 in different combinations. All right, so let's switch over to Onshape. Okay, so let's look at how this works in Onshape. We are going to be using all these lovely little mechanical bits and pieces to show you how these constraint types work. This will be in the 3D, and we're really just going to be marching along through all of these different mate styles. Okay, there's a whole lot here. Some of them are identical or very close to what we've already been talking about. The first one is the fastened mate. This is the same thing as fixed, fastened, fixed. They both start with F. And I love what it says here. You hover over it, and it says this removes all degrees of freedom between 2 parts. Okay, so you think about that. There are how many degrees of freedom in total? 6. Okay, you got to get that pounded into your head with this video. 3 translational, 3 rotational. And what a fasten mate does is it gets rid of all of that freedom. It's like the anti-libertarian mate. Okay, it gets rid of all the freedoms. And another opposite way to say this is that it introduces 6 reactions. It introduces 3 translational and 3 rotational reactions. Okay, those are like saying the opposite side of the coin, but just as accurate. So I'm going to go to this little puzzle piece that I built here. And I got to look for 2 like matching things that are easy to spot. So I would actually, I don't have really great internet today, but I'm going to go that corner right there. Come on. Oops. And then on the other piece, I'm going to go to the corresponding corner right here. Sometimes you got to zoom in and kind of wave it around like a magic wand before it does what you want. Okay, almost did what I wanted. When something like this happens, you can fiddle with the primary axis button. See that? If that doesn't work, start fiddling with the secondary axis button. Between the 2 of those, you can usually get it to where you want it, as long as you actually did choose the right locations. I'm going to accept that. And those 2 pieces are now locked together. I can wave them around, but they stay fixed together. It's just as though I had glued or bolted or nailed them together. That is what a fixed or fastened mate is. Okay, this is the pole cemented into the ground situation. I'll also show you what I talked about in the last part of the video. I right click and I go to fix. Now I get this cool little symbol pops up. Okay, this part is fixed. That means wherever it happened to be at that point, it's never going to move from there. If I grab that and try to wave it around, the symbol actually appears for me, showing me why I can't. If I grab this part and wave it around, it won't. I don't get the symbol because it's the other piece that it's fixed to. But yeah, those two are now locked down. And usually in Onshape, you want to pick one piece as like a reference and just fix it down somewhere. So all the other bits and pieces like hinged, moving parts, they will move relative to that without moving the main thing itself. Okay, we'll go on to the next one, the Revolute Mate. Feels like I'm in Australia. Where's the Revolute Mate? And this one is the same thing as our pinned or hinged connection. They don't use the degree of freedom language, but you can actually see in the picture itself, it's showing 3 of the translational degrees of freedom are not allowed. 2 of the rotational ones not allowed. We only have 1 rotational that is allowed with the revolute or with the pin. And we're going to do that right here. We're going to say right there. And let's see if I can make this work. I don't know if that's... well, I think what I'll do is I'll temporarily hide... I'm going to temporarily hide that part that I already selected. So there we go. You know, I think that's going to work. Nope. No. Okay, let's do it this way. I'll pick that one first. And then we'll hide that. Alright, that's good. You see how it's like the orange face of that is lit up. That's how I know I'm getting the correct thing. And I can see it here. One of the mate connectors is on hinge A, one's on hinge B. And let's accept that. Turn on visibility again. And let's just play with it and see if it works. Oh, okay. See, it's moving around, it's sliding around. So I actually want to let's take hinge B. That feels more like the base of it. Let's fix that down. And now we can grab, oh yeah, there we go. Lovely. Sometimes as well with these little revolutes, you want to actually put limits. You want to say only go between 0 and 90 degrees. Okay, let's try playing that now. And you'll see that it now does that. That's a very common thing, you know. That's when you like artificially want to tell the hinged part of the desk to only go down as far as when it hits a certain stop. It's not going to see that itself. You got to tell it where that is. This is not like a full physics modeling thing where it sees a solid object and hits it and stops up hard against it. You got to help it out. Okay, and then once again, now that I put that limit in, I won't be able to. I'm gonna remove that. I kind of like that when I could do everything. Oh, come on. There we go. I was just hitting undo then. Okay, next one. We have the slider mate. The slider mate, again, read this carefully. The parts can translate along the axis only. So how many degrees of freedom do you think are constrained? How many do you think are free? The answer is only 1 is free. 5 are constrained. Only 1 translational one is free. So I'm gonna use this one right here. Let's solid cylinder. Where are we? Okay, let's fix this part as the exterior, and let's. You know, often it's helpful actually to just pull the pieces apart to begin with, so they're not like overlapping. That's kind of what I ran into with that hinge then. I'm going to put a slider mate, and it slides, it's very important to understand this, it slides along the z-axis, if I'm not mistaken. So what you want to do, to make sure it slides in the correct direction, see the little blue z-axis? See how it's actually pointing in the direction that I want it to go, like up and down through that sleeve. If I hovered on this face, see the blue would now be pointing like through the wall of the sleeve, and that means the piece would slide, but it would slide in the wrong direction. It would kind of slide magically, ghost-like, in and out, left to right. But I want it to slide up and down, so I pick it right there. And then I go find my other piece. I find a matching location. All right. Okay, again, it didn't quite go where I wanted, so I'm going to play, I think that is, there we go. That was the secondary axis. That means it keeps the total orientation of the part as is, but it rotates it around the Z until I get where I want. And I will accept that, and then we'll test it out. Okay, great. Perfect. Okay, so that could be like the piston in a car engine, or the choo-choo train, you know, that steam thing that goes in and out, you know, the one with the guy. All right, excellent. And again, this would be a piece that I might, if I wanted to, insert a edit. I might put limits on it if I didn't want it to go too far. If I wanted to, like, say, you know, be physically constrained. Whoa. Interesting. That was weird. There we go. Okay, so I only want that piece to be able to go a little bit up and down. That's how you do that. Okay, let's see. I think, okay, sure, we'll do the planar mate. The planar one, I've never really actually had to use this, but this is for modeling something which is sliding along a surface. This is kind of like the simply supported, actually, sort of similar. For this one, I'm going to say it's this surface here, and it's this surface here. This is allowing two directions of translation, and I think no rotations at all. So this one constrains 4 degrees of freedom. Yeah, let's fix this. 4 degrees of freedom. There you go, see that? See, it's like it's sliding like the leg of a chair that can slide across the ground, but it's not going to come up off the ground, it's not going to go through the ground, and it's also not going to rotate. So that might be for like a simply supported piece in a machine that is like rubbing, is sliding along something, and that's all you want it to do. Like I say, it's kind of rare. Nothing I've actually ever used. Actually, what did it say there? Hovering, there we go. Can translate, yeah, okay. All right, this one is important, so I will do this one, and we'll actually finish with this one. This is the cylindrical mate. By the way, if you ever get to this point and you realize you should have clicked a different one, you can also choose differently from the list there. The cylindrical one is very much like the slider, except it kind of pictures like a round slider, like this one here, which, as you can tell in real life, would very happily, let's get this out of the way, would very happily both twist as well as slide. So think about it. How many degrees of freedom would this have? How many of the 6 are constrained? Well, the answer is that only 2 are free and 4 are constrained. This this piece can slide. Oh, hold on. Let's fix that. Hollow cylinder, fix. Okay, we can slide this up and down, but look at that. It also can twist around. Now, we would not have wanted this. Like, let's say I went back to the, where was it? The slider one here. Let's say I change that to be, what are we doing? Cylindrical, sorry, lost my train of thought. Let's say I change that one to be cylindrical. Look at that, now it actually does weird things. We don't want that at all. So we are going to undo. And I think I'm back to how I had it. Okay, we can grab that and we can twist it around. Again, I definitely would put limits on this because look, it feels like it should kind of hit that as it goes. So I would go in and I'd say, yeah, we definitely want some limits. Here I can actually limit. See, I need two pairs of limits because there are 2 degrees of freedom happening. So for these are the angles and this is the linear dimension. Let's try some things. It's often very hard to know in advance. Wow, it's twisting as it goes. Maybe I'll click solve. Yeah, I didn't like that at all. It went way too far. Oh, maybe not. Maybe that's actually, maybe I got right on the money there. Actually, that, yeah, I think I just coincidentally did that correctly. Okay, there we go. Cool, I like that. By the way, I didn't go into the constraints, but for the planar one, I think that would have given me 2, oh, 3. And they're kind of unlabeled. That's interesting. Okay, so here we had, I guess it's, okay, I wasn't expecting that. It looks like we actually have 3 degrees of freedom. We have 2 translational, the X and Y along the surface, but it looks like it's also allowing the Z twisting, and I don't know why I didn't see that. Let's try to twist that thing. Doesn't look like it's wanting to twist. Anyway, I'll have to look into that. Sometimes if you do animate, that's another interesting thing that lets you see exactly what's happening. Yeah, it looks like it's there. Watch this. Oh. Yeah, it's fine. Yeah, it's fine. I'm way out on a limb here. Okay, so there's our bits and pieces. Hope that hoping to see all the connections between, you know, walking around in the yard at school, doing the 2-dimensional analysis on the whiteboard, and then doing it here as well. We're talking about all the same things here. Sometimes the language is a little different, but it's the exact same principles over and over again. 6 degrees of freedom, 3 translational, 3 rotational, and we constrain those at certain times. And as I say, next week we'll show you more about how to calculate those 2-dimensional analyses and work out those reactions. All right, thanks guys. Have a good rest of your day.